session, let me just make one short announcement that we would like to take a few group photos of everyone. I mean, I saw people did it at Amplitudes and it was great. So just asking people, everyone, right before Andrea's talk to turn on their cameras, and then I will take a few screenshots. And because the audience rotates a lot in these online meetings, I will propose that we do it again before Juan's talk. And if I think that we don't have everyone yet, we will do it again on Friday. But I think twice should be enough. So today, before Andrea's talk, I'll ask everyone to turn on the camera. And as I said in the very beginning of the first day, people are welcome to keep their cameras on. I think it's more friendly and it leads to a more informal looking meeting. So don't worry about keeping your camera on during regular talks as well. And I pass it to Dima now.
Okay, so good time of the day to everybody. So today we have session on integrability. First we have Fedor, who will speak about separation of variables. So I was always curious from whom actually these have been separated. So maybe learn from him. Okay, Fedor, please.
There is some noise. Let's maybe mute everyone.
Yeah, so please, everybody, make mute.
Yeah.
Okay. So can you see the slide? I hope. Can you see the slide, Dima? Is it working?
Yeah, we can see you.
Yes,
okay.
We can. Yes.
Okay. So thank you very much for the opportunity to speak here. So I would like to speak about the results of these several recent papers with Kolya Gromov, Paul Ryan, Dima Volin, and Andrea Cavaglia, also a paper with Michelangelo Preti, and some work in progress. So another paper which hopefully should be out soon. So we studied the problem of separation of variables, which is one of the fundamental methods to solve integrable models, but it has been not much developed beyond the simplest GL2 cases. And we managed to solve a problem related to higher ranked models. So we managed to finally compute the measure in separated variables that should open the way to computing various scalar products. So I will speak about these results and later also some partial results for Fishnet theory with similar methods. So the main motivation for us is to develop new methods to compute the correlation functions in N=4 superrank-mills. And the idea is that, like in any integrable model, there should exist a basis in N=4 where the wave functions will become much simpler and just factorize. Like for hydrogen atom, they factorize in spherical coordinates. Here we expect there will be a basis labeled by x, the separated variables, where the wave functions would become a product of some building blocks, which in integrable models turn out to be Q functions. And here the exact Q functions should be given by the same equations that describe the spectrum, namely the very powerful quantum spectral curve equations that have found many applications for the spectrum. And in this way, we hope to link them with the much more challenging problem of computing correlators, which still does not have a fully satisfactory solution. So despite the fact that the hexagon methods and others have been formulated, they have many limitations, which we could hope to overcome. And the goal is to write correlators in terms of some combination, is to view the correlator as some kind of overlap between the wave functions of the states that would eventually be given in terms of Qs. And this picture has been around for some time, but recently in 2018, we finally managed to put it on a quantitative level, and we've, for the first time, found an example where to all loops you can compute the structure constant, although in a lattice limit, but to all orders in wrapping corrections. And it is given by a very simple scalar product between the Q functions of the three states. So this is for the cusp, for a triangle made out of three Wilson lines that form three cusps, which behave much like local operators, and the corresponding structure constant takes an extremely simple form in terms of Qs. So with the basis, so with this motivation, we would like to make progress. We would like to understand and develop separation of variables methods in general, and especially to move beyond the simplest models for which they have been much studied. So one of the key questions to compute scalar products and overlaps is what is the measure in these new nice variables. Like for hydrogen atom, we have a Jacobian in spherical coordinates. Here, when we do a change of basis, the scalar product would become something like an integral over these variables. And then one of the states is represented by one set of Q functions, and then another by another one. And then there is some measure, which is the Jacobian. So for GL2 type models, it is very well understood. So for non-compact spin chains, it takes this form, something like a van der Monde determinant. But higher rank GLN models are much more involved. And it was only recently understood how to actually factorize the wave functions precisely. And as far as the measure is concerned, it was not known at all beyond the GL2 cases. It was only known in the classical limit from some papers of Smirnov, Saifin, and some others. So in this talk, I will show how to solve this long-standing problem and how to compute the measure for quantum SUN and the SLN spin chain. So first, I will speak about the compact SUN case, which was done in this paper, and then I will discuss the non-compact SLN spin chains. So in fact, this was the case that we did first historically with Andrei Cavalli and Kolya Gromov. And then we extended these methods to compact case. And finally, I will speak about Fishnet theory and some applications there. So let me start with compact spin chains. So we are just consider first the spin chain in fundamental representation with a Cn space at each side. And then Hamiltonian is the usual Hamiltonian. But what's important is that for purposes of regularization, we also add the inhomogeneities and twist. So we consider the monodromy matrix built out of the usual R matrices with the generic inhomogeneities and the generic but diagonal twist matrix that gives periodic boundary conditions and makes the situation much less degenerate. So the spectrum in particular becomes simple. Then the transfer matrix gives commuting integrals of motion, and if we can diagonalize them by usual beta ansatz and so on. So how does separation of variables work here? For spin chains, we can now make a very precise statement that the wave function becomes a product of a very particular Q functions, the Q functions that encode momentum carrying beta roots. And this basis of separated variables is the eigenstates of the operator known as Sklyanin's B operator. So it's a commutative family of operators that are diagonalized at the same time. For SU2, it's just one element of the monodromy matrix, the usual one that also creates beta states. And one can see the spectrum is related to, of X is related to inhomogeneity. So they, in this way, we have 2 to the L possible combinations of plus minus, which give a basis of the full space. But then for SUN, situation is much more complicated. So B is now a polynomial in elements of T that was proposed by Smirnov, and then it was made more explicit in our paper. And we also realized how to actually implement the construction. So it's important to add an extra similarity transformation that we called makes the objects T into T good and B into the B good operator. Then it actually works, and one can find the spectrum of these separated variables. And also we observed that one can build the states in a very simple way for any SUN as an alternative to nested beta ansatz. So this, all of this was proven later in 2018 by Ryan and by Paul and Dima, and was also connected with another way to build the separated basis proposed by Maye and Nikoli that I will discuss in more detail later. So for SU3, it was also proven by Slavnov and Lyashin. So that's how to factorize the wave functions. But the overlaps for beyond the SU2 case of these X states with each other look rather complicated. And it's far from clear how to write some meaningful expression from them. So can we try to compute them indirectly? And that's the main idea that we used. So let me demonstrate how it works for SU2 spin chain for simplicity. But here it is quite simple, but it generalizes almost immediately to any SUN. So the idea is that since the different eigenstates are orthogonal, this should imply some orthogonality relations for Q functions. So if we look at the usual Baxter equations, so Q theta just encodes in homogeneities, and these are shifts. So then, and we just divide by some overall factor to bring it to this 4. So we have this difference operator. So then the main observation is that this operator is self-adjoint with respect to a simple scalar product. And so once we have this self-adjointness property, then we can derive orthogonality relations by the usual arguments from quantum mechanics. So what more precisely, we just define the bracket by an integral over a large contour that goes around all the inhomogeneities, and they just far away. And then one can immediately see that this operator will be self-adjoint. So why is that? If we just look at this thing where it acts on one test function, then if we look at this integral, we can do a change of variables where we transfer the shifts from one function onto the other one. And then remarkably, the coefficients here are constructed in such a way that we simply get the same operator acting on the other function. So just by a shift of the contour, we prove this self-adjointness property. And once we have that, it is almost immediate to derive orthogonality. So first observation is that we can introduce L such brackets for spin chain of L sides, where we just insert exponential measure, just an exponent of u, periodic function, which the Baxter equation does not feel. It's like a constant there. But the measures will become different. And now we use the quantum mechanical argument where we consider this combination, where we take two states A and B and consider the difference of these two operators. The difference comes from the transfer matrices, which encode the integrals of motion that uniquely identify the state, and so they will be different for different states. So, and this combination is 0, because on the one hand, in the first term, we connect with OA to the right and get 0, and in the second one with OB to the left, due to self-adjointness, again, it gets 0. So that's the main observation. And now once we plug in the definition of the transfer matrix, this becomes a linear equation on the differences of integrals of motion. So the coefficients here are just these integrals of pairs of Q functions divided by Q theta plus Q theta minus. So as you see, this is an integral over a big circle. It will be given by a sum of residues at locations of the thetas shifted by plus minus I over 2. So non-trivial solution, the fact that this system must have, when the two states are different, one of the differences has to be non-zero. So this homogeneous system needs to have a non-trivial solution. And that means that its determinant is 0. So we just find that this determinant should vanish whenever two states are different. In other words, it behaves exactly like a scalar product. So the proposal is that this is the scalar product in the SOV representation. So this is given by a sum of residues. So in the end, we get Q functions evaluated precisely at theta plus minus I over 2. As I said, this is the values of separated eigenvalues of separated variables. And so that is a very simple way to derive the scalar product in SU2 models, which also which matches known results that were computed a long time ago in the literature. And we get this nice determinant representation from the very beginning. So now for SU3 spin chain, what happens, the main difference is that now there are two types of beta roots, momentum carrying and auxiliary. So they are encoded in the Q functions with the lower index and the auxiliary in Q functions with upper index. And now we have two different Baxter equations, one for the Q functions with upper, another for Q with lower index, parameterized again by two transfer matrices in fundamental and antisymmetric representation. And like before, we observed that these two operators, so now they are not self-adjoint, but instead one is conjugate to the other. So again, the proof is exactly the same, just by shifting the contours. And so again, we can use exactly the same logic. We define L different brackets. And again, by exactly the same arguments, we find a linear system of equations whose determinant has to vanish. So now we have some more freedom. So we can couple different Q functions between each other. So there are some particular nice choices. And so we choose one Q function with lower index and two complementary Q functions with upper indices.
There was a question from audience, what is D operator?
Yes, sorry, I forgot maybe. So D is just operator of shift by I over 2. Thanks. So because of that, here this one of the Q functions appears with a shifted argument. And so in the end, we get 2L equations for 2L variables, which are these differences of integrals of motion. So we can write a determinant that has to vanish for 2 different states. So in this way, the natural proposal is that this should be the scalar product is this determinant of metrics of this kind. So the main 2 differences with respect to previous case are first that now we have 2 types of these auxiliary Q functions, Q2 or Q3, which carry dual beta roots. And the second, they appear not just like the first one, but with some shifts, plus and minus. So when we expand the whole determinant, it will be a sum with certain coefficients. So of Q's evaluated at these inhomogeneities, and the other Q's come in this combination, like a determinant, and evaluated at some shifted inhomogeneity. So, and we can immediately see that the first factor indeed matches the wave functions that I described from the construction of the separated variables basis. So the question now is there actually a basis in which the other state, the psi b, is given by this second factor? And that is quite non-trivial to answer, but the answer is positive. So we understood how to do it for SU3. So when we have these 2 states, one, they are represented by different sets of Q functions. And the first one is the overlap that I described before, but the second one should be the overlap with the dual state. So now this is a separated variables basis for the bra states. And the matrix of scalar products so can be found explicitly by computing their overlaps. So while the first set is the eigenstates of familia B of U operator, the second one turns out to be eigenstates of a new dual kind of operator, which looks very similar, again, built out of some determinants from the monodromy matrix. These U are the quantum minors, but now the shifts are slightly different, so it's a bit magical that this construction turns out to work, but it does. So the matrix of overlaps is just the measure is just the inverse to the overlaps of these 2 states. And we found in several examples that indeed it precisely matches the measure that we got from Baxter equations. So this puts the construction on a firm ground, and we find this nice determinant representation for the measure. So how do we actually build these states in order to prove all these statements? So one can build them following the approach of Maillet and Niccoli by acting on some reference state with transfer matrices evaluated in homogeneity. So in this way, we can generate not only this X basis, but also the dual Y basis, although in a more complicated way. So and to prove all these statements, so this diagonalizes the other dual C operator. And to prove all these facts, one can use the technology developed by Paul and Dima, which is highly non-trivial. So it's based on identifying some representation theory patterns here, and known as Gelfand-Zeffin patterns that label the states in an efficient way. And then one can write the commutation relations between all these B operators and so on in a meaningful way. So in this way, we can prove that indeed we can build a basis in which wave functions factorize in precisely the way we expected from this Baxter equations. So another comment is that for SU2 case, this matrix
question
of the
from audience, further question from audience, difference between tau 1 and tau 2.
So tau 1 is the monodromy matrix with auxiliary space and fundamental representation. And tau 2 is the monodromy matrix with the auxiliary space and twice antisymmetric. So together, the eigenvalues of these traces, tau 1 and tau 2, label the states uniquely. So that's why they appear here in our construction. Okay, so the important comment is that for SU2, this matrix that appears in the measure is actually diagonal. But for SU3, it is not. Nevertheless, it is describable in a simple way, just as this determinant of the integral. So I'd like to mention that recently there was proposed an alternative approach where one can derive some rather non-trivial recursion relations, presumably which describe the same measure, so in this indirect way by relating its elements to one another. So we have instead a direct formula for the measure elements themselves. So another comment is that we can compute not just scalar products of two states, but we can start taking some off-shelf quantities like form factors, and we can compute diagonal form factors where we take the operator to be the variation of integrals of motion with respect to some parameter such as twist. So I will not describe the details, but again, it is computed using the usual quantum mechanical logic of the kind of Hellman-Feynman theorem. And in exactly the same way, we get a determined representation for them. So as ratios of some determinants, and then the denominator, we have the same norm that I described before. So, and also all of these constructions generalize to SUN quite directly. So, okay, there is a more algebraic description which makes some things a bit more transparent and abstract at the same time. Let me skip that in view of time. So let me also mention that so chronologically, these kind of tricks with Baxter equations were used originally in this paper with Andrea Cavaglia from 2018. So then they were generalized to SLN and then to SUN. So next, a few words how this extends to non-compact SLN spin chains. So now the separated variables do not just take a set values in a finite set. Now they are taking an infinite set of values. So we get integrals instead of sums over them. So there we insert some periodic measure which ensures the convergence of the integral. So again, for SL3, for instance, we would like to have this kind of adjointness property. But now what happens is that since measure needs to decay exponentially, the price to pay is that it will have poles in the finite region of the complex plane. And when we move the contours to prove this property, we cross the poles. So one gets some non-trivial residues from the poles, which could spoil the whole construction. But quite miraculously, they all cancel precisely. So in the particular situation where we specialize to one of these functions being the Q functions, so they cancel due to some non-trivial relations between Q functions and the T functions. So and again, the whole construction then works exactly as before, and we view this constellation as yet another indication that we are discovering some natural structure behind the spin chain. So we get to the kind of structure here again, where this matrix, this measure is given by some determinant. So this determinant, one can see some structure in it that is rather similar to the conjecture of Smirnov and Tsaitin that was made long ago based on semi-classics and the quantization of the spectral curve. And now we can make a precise statement that agrees with that general expectation. Okay, so then in the upcoming paper, we also generalize this to any spin of the SLN representation. So now the measure becomes more non-trivial. It involves some gamma functions, and it matches needed to ensure that the operators are self-adjoint. And we reproduce precisely the measure obtained in the early 2000s by some rather much more non-trivial methods in this paper. So then again, we can actually show that there exists a basis in the Hilbert space where wave functions take the form predicted by Baxter's. Now the construction is more complicated. So to build the states, we need more involved T functions with non-rectangular Young diagram representations. So such technology was worked out recently by Paul and Dima and can be adapted successfully to this case. So the whole construction is put on the firm ground. And again, we checked in several examples that the measure we get from Baxter equations precisely matches the overlaps of these states. They now form some infinite matrix, but the elements match precisely. So finally, in the remaining few minutes, let me say about some early results and work in progress on extending this approach to Fishnet theory. So this is a strongly deformed version of gamma deformed n equals 4 sub Young-Mills, which itself has no supersymmetry but is integrable. So this has been studied for a long time, this theory. So the quantum spectral curve can be extended to it. And it has finite values of all these deformation parameters. So we still have integrability. So for instance, recently with Michelangelo Preti, we studied the particular notorious operator which is short, so it receives some non-trivial double trace contributions to its anomalous dimension, but nevertheless, quantum spectral curve computes them all very efficiently, as we demonstrated. So the Fishnet theory is actually yet another strongly deformed version of this model, to where we send the deformation parameters to infinity in such a way that they combine with the coupling. And in the simple case, we just get a theory of two scalar fields with a quartic interaction that inherits integrability and the quantum spectral curve. Also, one can derive its dual model almost rigorously, which is quite remarkable. And it reproduces this grid type of graphs that Malotchikov had studied a long time ago and which are integrable themselves in some sense. So in this simple playground, we hope to develop and understand how to compute the correlators by these new methods. So in order to regularize the model, it's important to twist the ADS spacetime symmetries to remove some degeneracy. It was understood how to do it in this paper. And then the setup becomes very similar to CASP. So one can study the basic operators trace of phi to the L. So in the simplest state is actually L equal 1. And one can use the same tricks with Baxter equations coming from the quantum spectral curve, as we did for spin chains. And in this way, first problem is to compute variation of the energy of the scaling dimension with respect to coupling. So and this gives the 3-point function of two identical operators in Lagrange. So that's the simplest kind of 3-point function. And the goal is to express this variation in terms of Q functions at fixed value of the coupling. Of course, one can write delta at any value of coupling from Qs, but we want to use Qs at a fixed coupling. It's not remarkable that a nice representation exists at all. So we found it's again some simple scalar product of Q functions, which moreover we can map in this simple case directly to the diagrams calculation and see that Q function actually encodes a set of resummed Feynman diagrams. So we are working on extending this to higher L, so to more general operators. The Baxter equation is known, it was derived in this paper. And so yet another generalization is similar kind of extension for the cusp. So where we have these three cusps with particular scalar insertions that correspond actually to length 0. So recently the Baxter equation was understood for higher length. So one can hope to generalize this simple result for correlators to more general insertions soon. And the main goal is to look at all of these examples in order to understand the structure and to see what kind of features emerge and eventually make a guess for the full n equal to 4 super Young-Mills theory. So here are some conclusions and the summary. I will just leave it here, and thanks for your attention.
Thank you, Fedor. Yeah, so we come to questions, but first I need to make a small disclaimer. So Fedor generously put me as co-author on the upcoming paper, but I actually was occupied with other business. And whether I will be a co-author or not depends on what will be inside the paper. And we have to discuss it and decide yet. So I do not want in front of 160 people being listed as co-author and be not co-author or not being co-author without doing inside something. So we're going to discuss. I just wanted to be clear on this. So go to question. It was a question from Ryo Suzuki. Just I will tell it quickly. So can you explain if it's off-shell, on-shell, 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 scalar products?
It's on-shell. So for the case when the states are actually orthogonal, so it's either 0 or non-zero. But well, in principle, it depends what you mean by off-shell. There are some definitions in the literature. One could adopt a different definition where you just take, instead of Q function solving the Baxter, some arbitrary polynomial Q functions and call this off-shell.
Not Fedor, you can put arbitrary Q function, right? I mean, anything.
Yes, so you could put arbitrary Q function inside the scalar product and call this to be the off-shell scalar product.
Then it's off-shell scalar product.
Yes, then it would be off-shell. Just what I mean, in the literature exists a standard definition of what people mean by off-shell beta states, and it's not precisely what we do here. But of course, it's not the only possible definition.
Okay, so I see the hand from Enrico. Enrico, please.
Hi, Fedor. So thanks for the very nice talk. And I wanted to ask, when you speak about Baxter equation and Baxter function and you compute correlators in fishnet theory, so which spin chain are you speaking about, or which representation of this spin chain are you speaking about?
Yeah, so presumably it should be the spin chain based on something like conformal group in the principal series representation. So what we did so far is that we just borrowed this Baxter from the quantum spectral curve, rather than constructing the spin chain more explicitly. So in fact, one can say some more precise statements and realize the spin chain at the level of operators, as was recently understood by Kohli and Amit in their paper about this dual fish chain. So now we have a firmer ground for the Baxter equation as well.
Okay. So basically, you are deforming the solutions from n equals 4, right?
Yes, yes.
Thank you.
Yeah. Charlotte?
Yes, a naive question. So among all your scalar products, you should also have the norm of the eigenstate somewhere.
Right,
So,
that's true. So that's an important point. So it would be interesting to link our results to the Gaden norm. One can hope that some link should exist. But at the same time, I should say we are not directly computing the scalar product between the state and its complex conjugate. So rather, we are taking some basis of right eigenstates of transfer matrix and left eigenstates of transfer matrix, normalized in some natural way from the SOV point of view. So then we get the scalar products, and it's non-trivial that there exists a simple representation for them, but we do not expect them to match immediately. It's just a basis of vectors and covectors at the moment.
yes, okay, I understand that, but it would be interesting to understand if there's some.
Yes, yeah, it's an important question, which I hope should have a meaningful answer.
Okay, thank you.
Vladimir?
You constructed the separation of variables for highest weight series, non-compact series. What are the perspectives for principal series or for the principal series representations?
Yes, of course, that's what we need for the fishnets. So what we see already is that the Baxter equation has the same nice properties, like all the self-adjointness and so on. It all works out. So hopefully there should exist an operator construction as well, which would work there. So presumably one expects there would be, like for the non-compact case, an infinite set of these separated variable states. So for highest weight, they extended only in one direction. Here, probably it would be just doubly infinite set.
Mm-hmm.
That's obviously one of the problems we are thinking about.
Is it helpful to have the same the separation of variables for open spin chain like we have, like you will see from
right? So this is not immediately clear. So how this would help, because here we have to diagonalize this complicated B operator. In the approach you are speaking about, you are diagonalizing minors, diagonal minors of the monodromy matrix, which are much simpler objects in a sense. But perhaps there could be a relation. Certainly, this one approach should teach us something about the other.
Thanks.
So currently, I don't see any other raised hands. If somebody wants to ask,
I have a small question for Fedor. Just very stupid question, but at a certain point, you say that the gamma deformation, strong limit of gamma deformation of n equals 4, or maybe even gamma deformation of n equals 4 is an integrable theory, right? So as far as I know, there are integrable sectors. For example, this operator that you have computed with Michelangelo from quantum spectral curve, and it's also possible to compute directly, at least in the strong limit. But what about this? This is not enough to say that the theory is integrable. I mean, what about operators with spins?
Yes, well, I would hope that the status is the same as integrability in n equal 4 super-Yang-Mills, where we cannot prove it, but we believe that it is integrable.
But you don't have any data.
I don't see a reason. There are some more subtle effects, like this mixing with double traces, potential violation of conformality, but it was recently observed that they all combine in such a way that, for instance, quantum spectral curve precisely describes the theory at the good conformal point, where all double trace terms organize nicely. So I don't see any indication that it would not be integrable in the same sense as n equals 4. There could be some subtle question about some logarithmic multiplets which remain to be understood. Well, apart from that, I think it should be fine.
Okay, so let's so for now it's okay for questions. We have to move to the next talk. So let's thank Fedor again. Yeah, so